Hello everyone and welcome to the new episode of our series of solving LeetCode Daily challenges. And today we are going to solve a problem called put marbles in bags, which is classified as hard problem, and it really is a hard problem. So without further ado, let's move to the problem statement. So we are given k bags, and we are also given an array of weights. And this array of weights basically show us the weight of a marble. And we need to divide the marble among the k bags according to some rules. So the rules are that no bag is empty, so we need to put something in every bag. And if the i's and j's marble are in a bag, then every marble between them is also in the bag, which basically means that we should split our marbles into consecutive segments. Okay, and if a bag consists of the marbles from with indexes from I to j inclusively, then basically the cost of this bag is defined as weights I plus weights j. So we only care about the first and the last element in the bag. Okay, so the score of distribution is defined as the sum of the costs of all of the bags, and we need to return the difference between the maximum and the minimum possible scores among all of the distributions. Okay, let's look at the statements. Let's look at the constraints. And the constraints are quite high. Our number of marbles is up to 100,000. And our k is also up to 100,000, and the weights are also pretty big. So this rules out a potential dynamic programming solution, because you can imagine a solution with complexity of big O of n times k, where n is the weights length, which is a dynamic programming solution with a state of basically, okay, I'm currently looking at the marble with index I, and I've already collected k bags and my current that's basically it. We don't need anything else in the state, but it will be too slow. So this means that we need to come up with something smarter, and it's not easy, especially during an actual coding interview. I think if your interviewer gives you such a problem, then probably he or she expects some really good knowledge from you. So it's not an easy problem. However, let's try and solve it. So the easiest way to explain the solution is probably to show the example. So suppose we have k equal to 3. So we have 3 bags, and the weights of marbles are like this array of 1, 2, 5, 4, and 3. And let's define the concept of a border. So the border is basically like an imaginary concept of like bag border, and this border defines where the previous bag ends and the next bag begins. So for example, here we have these 2 borders, and they define the distribution among 3 bags, where these 2 elements will be in first bag, this one element will be in second bag, and these 2 elements will be in third bag. And it's worth mentioning, it's actually mentioned in the example that if we put only 1 marble in a bag, it's counted twice towards the cost of the bag. So for example, the cost of this bag is equal to 2, because 1 plus 1 is 2. Okay, so let's define, and as you can see, we can choose these borders independently from one another. And if we have a k equal to 3, selecting 2 borders will uniquely define the distribution, a valid distribution. Okay, so let's come up with another definition, which is a cost of a border. And I'm stating that the cost of the border is the sum of the 2 elements that are adjacent to this border. So for example, the cost of this border is equal to plus 5, which is 7. And why is that? Basically, if we have a border in this position, then the previous element will be the end of some back, therefore it should count to the cost of the distribution, and this element will be the first element of the next back, and because of that, it's also should be counted in a cost of a distribution. And yeah, as I've said, we can select these borders completely independently from one another. So the proposed solution goes like this. Let's, for a given array of weights, let's calculate the array of borders costs. And it's equal to 3, then it's equal to 7, then it's equal to 9, and then it's equal to 7 again. And yeah, we have this array of borders with the lengths of exactly n-1. And here comes the solution. We actually can use a greedy strategy here. Since we can choose the borders independently from one another to calculate, let's say, the minimum cost of distribution, we can just take k-1 minimal elements from this array of border ways. So in this case, it's 3 and 7. And to calculate the cost of the maximum distribution, we should take two maximum values among borders cost. And in this case, it's equal 7 and 9. This is true because you can see for yourself that cost of the distribution is basically the cost of the weight of the first element, because it will always be the first element in some back, plus the weight of the last element, which will always be the last element in some back, plus sum of all border costs that we have used. Okay, so let's look at the example for this case. Let's find the minimum and the maximum cost. So as I've said, the minimum cost is achieved when we choose the borders with weights 3 and 7. And to do that, we should, for example, put our borders in here. And then the cost of this distribution is equal 1 plus 1, which is the first box, plus 2, which is the beginning of the next box, plus 4, which is the end of the second box, plus 3, which is the beginning of the first box, and plus 3 again because it's the end of the last box. And our total cost is equal to 14. And in the parentheses, I've taken these costs of the borders that we have selected. So this is the border of the cost 3, and this is the border of the cost 7. And now let's do the same for the max cost of the distribution. So our max values are 9 and 7, and we can achieve this by putting borders in here and in here. Then our max cost is equal to 1 plus 5, which is the first box. Then it's equal to 4 plus 4, which is the second box. And then it's equal to 3 plus 3, which is the last box. And once again, in this parenthesis, we can see the cost of the borders that we have selected, which are equal to 9 and 7. And in this case, the cost is equal to 20, and the difference is max cost minus my minimum cost, which is 6. And that's pretty much it. So after you came up with this not very easy solution, you have to implement it, and the implementation is comparatively really easy. So we will define the list of borders. Basically, it's the cost of every border, and we will calculate these costs as the sum of two adjacent elements. Then we will sort this list, and then basically our minimum sum is the sum of the first k-1 elements in this sorted array, and our maximum sum is the sum of the last elements in this sorted array, and then we can just return the difference between them. And yeah, our first and here, like, I defined the cost of the distribution as first element plus last element plus sum of these border costs. But when we will substitute max cost minus minimum cost, these two values will cancel out and they will be equal to 0, so we don't care about them. And that's why we can just calculate the weights of the borders. sum them and just substitute the minimum sum from the maximum sum. And that's it. Okay, what's the complexity of this solution? The hardest part of our solution, like operation-wise, is sorting, and there are a lot of quick sorts that work with complexity of big O of n times logarithm of n. And that's the complexity of our solution. Okay, what lessons can we get from this problem? So I would say that if you get this problem during the technical interview, then the best strategy for you, if you cannot come up with a solution right away, is to tell your interviewer what solutions you do know, what solutions you can implement right now. For example, you can mention the dynamic programming solution, and it will be a huge plus for you, because your interviewer will see that, yeah, this guy knows what's a dynamic programming. He or she knows how to implement it, which is pretty cool. And yeah, this problem is not hard, and sometimes you have to like roll with it. If you are given a bad hand in a poker, you can just like make the best out of bad situation. And here it's basically the same. Or if you are smart enough to quickly come up with the solution, then good for you. Because yeah, I think that during the real interview, it would be really, really hard for me to come up with the solution quickly, because yeah, I spent some, I don't know, 20 minutes thinking about this solution behind the scenes. Okay, guys, thank you very much for your attention. I hope you enjoyed the problem and my explanation. If you did, please press like, subscribe, and I hope to see you tomorrow. Have a nice day. Bye.